Okay, our third speaker of the evening is M.Z. Naser, an assistant professor at Clemson University focusing on causal and explainable artificial intelligence in structural engineering and material science for sustainable infrastructure. Naser is a member of Artificial Intelligence Research Institute for Science and Engineering, ARISE. He's the chair of ASCE's Advances in Information Technology Committee and various editorial boards and building committees. He's co-authored 100+ papers and 3 books.
So to start with, it always helps to see how much big data we have. And if you look closely, an average firm in civil engineering can have this much data. 125,899,906,842,624 bytes. If you try to print this would be about 500 billion pages. Just one firm, 1 year. So we have so much data in civil engineering. The interesting thing is the following. In 2017, we only use 5%. So out of everything we have, we use 5%. And we can do all these great things we have, which is really great. 2023, we use 96%. We use 4%, so we throw away 96%. And we still can do the great things we can do. If you look at the industry-wise, we spend about 30% of our time going through data. This is how much time we waste. 30% of companies and firms, engineering firms, they don't really use AI or they don't use software that can seamlessly mesh together. So they use different softwares and they spend different time trying to adjust these softwares. This becomes a big problem, especially if we have so much data that we can use. So to go back a little bit, usually what we normally do is the following. We have a phenomena we're interested in, for instance, decarbonization, assessment of bridges. What we do is we have a test, we observe a response, and then we try to create a tool, an equation, a chart, or a model to figure out what we can do from there. More recently, we started saying, and some of the things that we can think about is the following. If you use tests, most likely you're going to be spending resources. You're going to have to spend a lot of time, a lot of money. If you use simulations, we don't really have a standard software. We don't have a standard procedure. We don't have a way to figure out what can we use for inputs and outputs. So this also becomes a problem. If you go even one step further and start to talk about statistics or advanced statistics, this is what we have. What we have is we have a methodology and we have assumed conditions. One of the biggest assumed conditions of all time is we assume linear regression or linearity, which means this. Plus, factor 1, factor 2, and so on. The biggest problem with this is the following. You're inherently starting at a disadvantage because you're already assuming everything fits a linear relationship. You're also assuming that the relationship is exactly linear, which in real life, as we all know, it's not really linear. So you start with very poor assumptions, you fit data for these assumptions, and you end up with an equation that you can add to a building code, and you can say everything works nicely. If you step back, you see that we have a lot of issues with statistics, which if you take it to experiments or simulation, will also grow into bigger and larger problems. So what we can do? Well, this is where somebody would say, well, we have so much data, we can use AI. Great. So when we use AI, we know AI or ML is really, really good at predictions. My colleagues here have shown great examples, massive data sets, scale, small data sets, work very well. The question we always have is the following. If machine learning can predict X could be anything. Strength, properties, condition, whatever it is. The question becomes, if AI or ML can predict X with very, very high accuracy, as we have seen, does this mean that AI can come up with a theory for how we can predict this thing? Because if it can predict it very, very well, if we go back to AI and figure out how AI was able to predict it so well, we'll learn something new. This is where we can discover new knowledge. So maybe even some theory. So what we normally do is we have a data-driven approach, collect data as we've seen millions of data points, train some machine learning models, have predictions, and try to play as much as you can to have very, very high accuracy. Most of the time it works. Sometimes, as colleagues have shown us, some problems it doesn't work, many others it does work. The problem is we're always going to have one question, how AI was able to come up with this very, very high prediction. So what we can do, somebody would say, well, let's explain AI, and this is where something like explainable AI becomes a fancy thing. Explainable AI is the way that AI can tell us, this is how I arrived at this prediction. For instance, this is how I use these inputs, and I came up with a strength of 5,000 psi. The interesting thing is the following. Sometimes AI's predictions may match what we know from physics, sometimes it doesn't. So although it doesn't match physics, it can still get very, very high accuracy. This can give you a question. Well, if it can get high accuracy, without the physics that we know. So how was it able to predict this high accuracy? It's interesting, right? It makes you think. So this is where the presentation actually starts, and we start to think about some examples. I have a very quick question. Question, does more PhDs in civil engineering lead to more collapsed structures? Yes or no? Yes? No? We'll see. So what we did, we actually went to the literature and we collected real data. And the data comes from NSF, National Science Foundation, as well as this very famous paper on ASCE, more than 500 citations. This is what we see. If you look at number of PhDs, purple series, number of collapsed buildings, blue series, you can see that the correlation is 85%, 84.9. So to answer the question, is more PhDs cause more collapsed structure, the answer is clearly yes, right? Because they go hand in hand. If you look at bridges, we see something much more interesting. For the same time periods, we see that the correlation now drops 20%. So is it yes or is it no? What we normally see is this. AI sees this. It sees data between some data points. Real life is the following. Our data is much larger. We only have a small glimpse of it, no matter how much big data you're using, right? And this is what we use to train AI. And of course, we can always have limitations. Every method has positives and negatives. Empirical methods, traditional methods, experimental methods, even AI. But having something like this gives you something very interesting. It gives you the following. If there is one thing that you can take, and I think my colleagues stole this from my Thunder Life, correlation does not imply causation. This is the biggest thing that we can think about. Now, this is what AI can be interesting. Many years ago, Da Vinci says the following. There is no result in nature without a cause. Understand the cause, and there is no need for experiment. If you know why something happened, why do you have to test for it, right? You know what it is. So causality or causal machine learning is basically the way or the science of understanding cause and effect. If you understand the cause and effect, not the correlation between two things or 20 things or 50 things, then we start to come up with something much more physical, something that's much more important. This is what we normally do. Left figure. We have parameter 1, parameter 2, parameter 3. We just have them in the data set, and then we assume train machine learning. We have an output, y. Real life is the following. X causes 2, 2 causes 3, 2 causes y. We have some hidden factors we don't see. Without knowing those, we can't really see the picture. Traditional statistics, traditional machine learning, traditional experiments, causal machine learning. So there is a big philosophical jump between what we have or what we can do later on. So the important thing is the following. No matter how much data you have, machine learning can only give you association. Association is basically the following. It tells you, I have seen this data and I'm associating parameters, and hence I can predict X with this or Y with this accuracy. Real life, we have interventions. If you have an experiment, let's say a beam, and you would like to build another beam that's identical to the first beam, both beams will behave similarly. If you change one parameter about one beam, you're going to expect some change in behavior, which we could easily figure out. What happens if you change 5 things in one beam? Would you be able to figure out which parameter causes what? It's going to be very hard, and hence we have to go for something like interventions or counterfactuals when we go and use advanced machine learning or causal machine learning to figure out what could happen, what would happen if we change something. So it's always good to visualize something, and in this case I chose a very simple problem. The problem is the following. Imagine we have a concrete beam, and all our problem is, can we predict when this beam would fail if we have fire? Is it going to fail an hour, 2 hours, 3 hours, or 4 hours? So we've done some research, we've collected data, we published something. I have 4 figures here. 3 of these figures are predictions from 3 different codes, international codes, and 1 from machine learning. Can you guess which one is from machine learning, which one is from the other codes? Is A from machine learning? B, C, or D? A, B, C, D. A is machine learning. These 3 are from 3 different international building codes, including AC. I'm not going to say which one it is. So as you can see, we have very interesting results. Machine learning was able to predict things that's a very complex problem very easily. 3 different building codes that are used in 3 different continents. 2 of them did to some extent. 1 was horribly off. But this tells you something interesting. It tells you we have a tool, machine learning, that can predict something very, very accurately, and we don't know how. We don't know why. So how would you trust such a thing? This is where you have to go back and say, okay, well now correlation is really good because I'm solving a problem, but I would like to know why, so I can go back and update this building code. We can have safe structure, right? So you could use different ways to explain machine learning models, and they would say, well, I arrived at this prediction, for instance, because the concrete cover was this much, or the loading was this much, which a lot of these things make sense from a physics point of view. Some of them don't, and we still have very good accuracy. So this is where you have to go back and realize, well, there is something that's awfully different about the way we perceive AI versus the way that we should use AI. If you use the same data, same analysis using causality or causal machine learning, you're going to have something like this. If you look at these parameters, you can see that all the linkages are straight lines without any arrows, which basically tells you that machine learning is able to predict this phenomena as well as many, many other phenomena, but it cannot tell you how it does it, or it cannot explain its predictions. So there's going to be a fine line between how do we know, we know machine learning works very well, but we're not really sure how does it do what it does. But if we can know how, then we can go back and update a lot of the theories we have, a lot of the information that we have. And here's my last slide. So machine learning is picking up. There's a lot of interest. There's a lot of publications. We've recently, my group, we published a textbook. You don't really have to buy the textbook. We have all the material open access free online. So if you go there, you can just download them, you could use them, you can learn from them. You don't have to worry about everything. We have lecture notes, we have Python code, we have data sets, we have Excel sheets. Everything is free. Everything is. If you're interested in machine learning, we have two projects with Elsevier as well as with ICE, institutions of civil engineers in Europe. They're trying to build a new handbook for AI for civil engineers. For instance, if somebody would like to use AI in the industry, how to use it. I'm the chair of ASCE, Advances in Information Technology. We're working on a manual of practice because we would like to have a procedure and a methodology to how to use AI in civil engineering for concrete, for steel, for different structures. Because without having so, it becomes a big problem because everybody will be using their own thing and then it becomes a bit hectic to go back in time and figure out what to do. I hope this was interesting, and I'll be waiting for your questions. Hopefully, thank you very much, and thank you for our colleagues for sponsoring.